Okay, so on the first page, we talked about a couple of ways of finding derivatives that were very easy involving lines. But let's generalize that to any polynomial expression. So this is known as the power rule. And here it is. If n is a rational number, then the function f of x equals x to the n is differentiable, and its derivative is equal to n times x to the n minus 1. Note, each term can only have one variable. It must be expressed in the numerator, and it must be calculus friendly. And we'll talk about what those three elements mean as we look through some examples. So this looks a little scary, and that is what the formula is. So you're probably thinking, geez, I'm not sure what I'm supposed to do here. But if we really look at where those letters end up, the variables, we start off with x to some power, and in the derivative itself, that power of n ends up down in front. We rewrite the x, and then the power is diminished by 1. So if it had been a 10, it will become a 9. If it was a 2, it will become a 1, etc., etc. It does get a little complicated when you have fractional exponents, but we'll talk about that when that situation arises. So for number 9, we have f of x equals x to the 6th. This is something that's eligible for the power rule. So what I'm going to do is start off with my notation. F prime of x is equal to, so that power of 6 is going to jump down in front. I rewrite the base of x, and then the power of 6 diminishes or decreases by 1 to a 5. That's an implementation of the power rule, and that is your derivative. That's all there is to it. In number 10, this one's a little bit trickier because in its presentation it is not calculus friendly. So what I need to do first is work with this radical and rewrite it using fractional exponents. So another way to write this would be x to the 1/5 power. These two expressions are equivalent, but it form fits now to the power rule. We have a base of x, and we've got some power that is a rational number. So now I'm going to implement the power rule. So g prime of x is going to equal, that power leaps down in front, I rewrite the base, and I diminish the power by 1. So 1/5 take away 1, and because this is our first time doing this, I'll show a little bit of work. 1/5 take away 1 is the same as 1/5 take away 5/5. And that's going to leave us with -4/5. However, in most calculus textbooks, you're not supposed to leave an answer with a negative exponent. So we'll just have to implement the basic Algebra 1 rules of exponents to correct for that. So in the end, we end up getting g prime of x is equal to 1/5x to the 4/5. So we've corrected for the negative exponent by moving the term downstairs into the denominator. All right, so that was your example number 10. Let's go to number 11. Y equals 1/x to the 4th. Well, for you to use the power rule, the x must be in the numerator. And right now our x is in the denominator. So I have to make it look like x to some power. In number 9, we already started off with that condition. Here we had to do a little bit of a rewrite to get x to some power. Well, this is not x to some power on the top anyway. So to make it look like that, we're going to move it up. And we're going to say y equals x to the -4. Now we have it looking like all of the other ones. So now I can use the power rule. So y prime is equal to, that -4 is going to leap in front. I write the base of x, and I decrease -4 by 1. If you think about -4 on a number line, and you decrease it by 1, that means you're moving to the left. That's what it means to decrease. So you're going to end at -5. But once again, you can't have this negative exponent, so we correct for that by moving it downstairs. Negative 4 over x to the 5th. All right. And that's all I want to say right now about the power rule.